by far the hardest class of reactions to balance are the redox reactions. Now, when I say redox reactions, I'm actually kind of referring to a specific subset of redox reactions. See, there are a lot of reactions that are redox reactions. If you look at combustion, we have oxygen, O2, oxygen's in a zero oxidation state, and when we combust something, we generally have something bound to oxygen that takes oxygen to a negative oxidation state. So when I say redox, what I'm typically referring to are things where you see ions in solution exchanging electrons with each other, as well as changing what they're bound to in terms of oxygen and hydroxides. So this special class of redox is one that is typically solved by using what's called the half reaction method. And what the half reaction method does is that it breaks balancing the number of atoms of each element and the number of electrons into two separate steps. So we'll start out with a simple example, and then we'll move to a much more complicated example. So a simple example here, we have iron plus 3 AQ plus copper plus 1 AQ goes to iron plus 1 AQ plus Cu plus 2 AQ. So we have iron plus 3 ions in solution with copper plus 1 ions in solution, and they're exchanging the electrons to give us iron plus 1 and copper plus 2. Now superficially this reaction looks balanced because you have 1 iron on the left, 1 on the right, 1 copper on the left, 1 copper on the right. The problem here is that we have 23 electrons in iron plus 3, 28 in copper plus 1, 25 in iron plus 1, and 27 in iron plus 2. So if we add these together, we've got 51 electrons on the left and 52 electrons on the right. So we created an electron spontaneously if we've written it this way. So this reaction is not actually balanced. So how do we balance it? What we're going to do is we're going to look to split the reaction into what are called half reactions. And each half reaction basically describes how an element is gaining or losing electrons. So we need to identify two types of reactions in our equation. The first is going to be the oxidation reaction. This is going to be the reaction where an element loses electrons. So here we have copper starting out in a plus 1 oxidation state going to a plus 2 oxidation state. So in this case, copper has lost 1 electron. And this is going to be our first half reaction. Copper plus 1 goes to copper plus 2. If you ever have anything being oxidized, you always have to have something being reduced. And the reduction reaction is going to be the one where we have an element gaining electrons. So we've got iron plus 3 going to iron plus 1. In this case, iron gained 2 electrons. For the half reaction method, what you're going to do to balance the electrons is you're just going to manually add electrons to the equation. So again, what we have here is 23 electrons in iron plus 3 and 25 in iron plus 1. So we need 2 more on the left. And to do this, we're just going to add 2 electrons to our equation. For copper, we've got 28 electrons on the left and 27 on the right. So we're going to add 1 electron to our reaction. For any oxidation reaction, your electrons are going to appear on the right. For any reduction reaction, your electrons are going to appear on the left. Now what we want to do is take these 2 reactions and add them together in such a way that we cancel out the number of electrons. So the top reaction only has 1 electron, the bottom has 2. So if we just multiply the top reaction by 2, 2 copper plus 1 goes to 2 electrons and 2 copper plus 2, and we add the 2 of these back together, our electrons are going to cancel. And what we're going to get is iron plus 3 plus 2 copper plus 1 goes to iron plus 1 plus 2 copper plus 2. In this case, we have the same number of electrons on the left and right as well as the same number of elements. Now this is a very simple problem. So how do we make it much more complicated? Let's say we take the reaction iron plus 4 AQ plus copper solid, so copper metal, goes to iron hydroxide solid plus Cu2O solid. Now what you're going to notice is that off the bat I can't balance this because I've got oxygen and hydrogen on the right, but I don't have any sources of oxygen and hydrogen on the left. This is a big red flag that you've got a redox reaction that has to be done by half reactions. You won't always be given the water or the protons to balance it out. So what's the procedure for solving a really complicated system? Well, the first thing you want to do is you want to figure out the oxidation states of all the elements. Now, typically oxygen and hydrogen, oxygen's going to be -2, hydrogen's going to be +1. So unless you have a reason to think otherwise, those are pretty much solved for you. Now, if we have an ion in solution, something like iron plus 4, the oxidation state is just the charge. So this is going to be a +4 oxidation state on iron, Pure element by itself, oxidation state is 0. Iron oxide, we've got 3 hydroxides. Each has a -1 charge. This is going to be iron in a +3 oxidation state. We have Cu2O, oxygen is going to be in a -2, so we're going to treat copper as a +1. If you're not comfortable with figuring out oxidation states, click the link. You'll be able to find a link back to figuring out how to do oxidation states. A bit outside the scope of this video right now. But we finished our first step. We figured out the oxidation states of all the different elements. Next thing we want to do is figure out who's being oxidized and who's being reduced. So in this case, we have copper going from 0 to +1. So in this case, copper is being oxidized. And if we have something being oxidized, we have to have something being reduced. So we've got iron going from +4 to +3, so this is our reduction reaction. Again, remember, oxidation is losing electrons, reduction is gaining electrons. Now we're going to split these into 2 separate reactions. So we've got iron +4 going to FeOH3. So we're going from a +4 to a +3. For our copper, we've got copper going to Cu2O solid. We, in this case, have copper going from a 0 to a +1. Next step, we want to balance the elements that are being oxidized or reduced. We don't care about oxygen and hydrogen yet, that's a later step. So now we have 1 iron on the left, 1 iron on the right, so we're balanced. On the copper side, we've got 1 copper here and 2 over here. So we're going to need to balance the copper by putting a 2 in front of it. Now that we've balanced the elements being oxidized and reduced, the next thing we need to do is put in the number of electrons corresponding to oxidation and reduction. Now iron's pretty straightforward. You've got a +4 here going to a +3 here. So you need to add 1 electron to the left. And this 1 electron is going to compensate, to basically be where we get our electron from for the iron. For copper, we're going from a 0 to a +1, so that's 1 electron, but we've got 2 copper atoms doing it. So it's going to be the change in oxidation state times the number of atoms of that element. So in this case, we have a change from a 0 to a 1, so that's 1 electron, and we've got 2 copper atoms doing this, so this is actually going to give us 2 electrons. All right, next step. We need to be able to add these 2 back together in such a way we cancel out the number of electrons. We've got 2 being transferred here and 1 being transferred here. So our solution now is to multiply the bottom reaction by 2. So we got 2 Fe +4 plus 2 electrons goes to 2 FeOH3s. Now that we've got the electrons balanced, we've got our oxidized and reduced species balanced, next step is to add these 2 reactions back together. So our number of electrons here are going to cancel. And we're going to be left with a 2Cu, a 2 Fe +4, and a 2 Fe2H. This is basically just adding these 2 reactions together. Now that you've got the reactions added back together, the next step is that you want to balance the oxygen. We're only going to focus on the oxygen. So if we erase our half reactions, just for clarity, and we start counting it up. On the right side, we've got 2 FeOH3s and we've got 3 hydroxides. So this is going to give us 6 oxygen atoms from this molecule and 1 oxygen atom from this molecule. On the left side, we don't have anything. What we want is to have the same number of oxygens on the left and the right side, and to do this, we're going to add water until we have the correct number of oxygens. So on the right side here, we've got 7 oxygens, and so we're just going to add 7 waters. Now, for whatever reason we had oxygen on the left side, we wouldn't add 7 waters. We'd add just enough waters to get the number of oxygens equal, and we'll see this when we do hydrogen. So now that we've got the oxygen balance, now we have to balance the hydrogens. And to balance hydrogen, what we're going to do is we're going to add H plus whatever side of the equation doesn't have enough hydrogens. So if we look on the left side, we've got 14 hydrogens due to water, nothing else. On the right side, we've got 6 hydrogens due to this iron hydroxide complex. So we need to add an additional 8 hydrogens to the right side in order to balance it out. And to do this, we're going to add H+. So we've got 7 waters on the left now, 8 H pluses on the right, is everything balanced? Well, yes. At this point, you've hit the final step. The electrons being transferred are balanced, the oxygens are balanced, and the hydrogens are being balanced. And so at this point, we have finally balanced the reaction.